Today let us talk about the work done by a spring. Let us see how when a spring from its natural length is stretched or compressed by using an external force, in the process the spring also does work, right? Because as we know the nature of spring force, whenever a spring is elongated from its natural length or compressed, it creates a restoring force, yes, given by Kx, where x is the extension or the compression in the spring. And as the object m, the block of mass m which is connected with the spring that moves, it undergoes a displacement. So there is a work done by the spring on the block, right? As we do this exercise, we shall see that whether you stretch a spring or you compress a spring by exerting an external force, in both the cases the work done by the spring on the block comes out to be negative. We shall see how that happens. So we first talk about the work done by a spring when it is stretched. So as you can see here in the figure, there is a block of mass m connected with a spring of spring constant k. The spring in the first figure is in its natural length. So this is the position x is equal to 0, where the spring is in its natural length and the block will be in equilibrium. There will be no force initially acting on it. And now this force F comes and acts on the block towards right and tries to take the block towards right. It displaces the block. As the block gets displaced, see that the spring gets stretched, and at a moment when the block has got a displacement of x from its mean position, we understand that the spring force acting on the block would be Kx, isn't it? And the direction of this spring force Kx will be opposite to the displacement. The block has displaced towards right, the spring force will be towards left on the block, right? Now since x changes continuously, the displacement of the block is changing continuously, as well as the extension in the spring is constantly changing, we understand that this force Kx, the spring force, is a variable force, right? And in order to find out the work done by the spring, we have to use the method of integration. So what we do is, we assume that let's say when the block is at this displacement x and it undergoes a very small further displacement dx. In undergoing that displacement, the small work done dw by the spring would be the spring force, which is Kx, times the small displacement, that is dx, into the cos of the angle between the two. Now see carefully that Kx is acting to the left and dx is to the right. So the angle between these two vectors, the force vector and the displacement vector, will be 180 degrees. And that gives us the small work done dw as minus Kx dx. And now what we need to do is, we need to integrate this expression to get the total work done. So w, the total work, will be integral of dw, which will be nothing but negative of integral of Kx dx. And we can put the limits of integration as well. The block started off from x is equal to 0. And let us say finally the block reaches a position x is equal to x naught, the final displacement of the block, which will also be the final extension of the spring. So that is this. So now we can integrate this expression. Minus and k will also come out of the integral because it's a constant. When we integrate x dx, we know that we will get x squared by 2 as the integral. So this will give us minus k x squared by 2, and now we put the limit 0 to x naught, which will give us minus k x naught squared by 2 as the work done by the spring. So we can write this as w is equal to minus half k x naught squared. See that the work done by spring comes out to be negative. The simple reason behind this is that the displacement of the block is opposite to the direction of the spring force. Force and displacement are opposite to each other, right? This is when the spring undergoes an elongation, it is stretched. Let us see a similar exercise, let us do a similar exercise when the spring is compressed instead, by exerting an inward force. So there is an external force which acts towards left now on the spring and creates a compression in the spring. So if we assume that when the block is at x is equal to x, we understand that the compression in the spring will also be x, and corresponding to that, the spring force which will be coming and acting on the block from the spring, let us draw it on this side. Here the spring force comes from the spring, so it's here. it is kx towards right. The external force F is, by the way, still available, so it's still there, present there. But since we are looking forward to find out the work done by the spring, we will consider only the spring force, which for assuming that, let's say, the block undergoes a very small displacement dx further from x, can we say that the small work done by the spring dw will be the spring force kx into the small displacement dx into, once again, do we see that cos of the angle between the two force and the displacement is 180? The spring force is towards right, whereas the displacement of the block is towards left, right? So once again we get minus kx dx as the factor which is to be integrated now to get the total work done, which will be nothing but integral of dw. So minus integral of kx dx, assuming that once again the block was taken from x is equal to 0 to x is equal to x naught, we see that we will get the exact same expression, minus half kx naught squared, as the work done by the spring that we have obtained above, which is similar, which is the same as the expression obtained above, and for the same reason that the spring force acts opposite to the displacement. So there is an important thing that we understand here, that whenever a spring is either compressed or stretched from its natural length, from its equilibrium state, the work done by the spring is always negative. Okay. So having understood this, having known the work done by a spring, let us take an example to make things more clear. So there's this question which says a block of mass m is attached to a spring with a spring constant k. An external force F creates a constant acceleration A in the block. Calculate the work done by the external force in moving the body by a distance d. Now looking at this carefully, there is an external force F which acts on this block towards right. Understand that as this block starts moving towards right under the effect of this external force, the spring will stretch and will create its own spring force kx in the leftward direction. And do we understand that as the block moves towards right, x keeps on increasing, thereby continuously increasing the spring force? If the spring force continuously increases, then the net force acting on the block at any point in time, F net acting on the block at any point in time, will be given by F, the external F, minus kx, isn't it? And net force acting on any body should be equal to the mass of the body times its acceleration by the Newton's second law. So this is the equation that we get for the block's motion at any point in time. Now there is one important aspect mentioned in the question, that is that the block moves with a constant acceleration A. This A is a constant. What does that tell us about the external force F? It tells us that F is equal to ma plus kx, right? From this equation, if we take this kx factor on the other side, this is what we get, and this is an important information that we are getting. We are understanding here that the external force F acting on the block is not a constant force. It is given by ma, which will be constant for a given A, but kx is constantly changing, right, as the block moves towards right. So this force F acting on the block is not a constant force. It's a force which is increasing continuously as the block is undergoing a displacement towards right. Okay, so this is the important aspect of this question. This is what makes this question tricky. So now that we have got this expression for force and we understand that this is a variable force because of this factor kx, we cannot find out the work done by this force directly. We have to use the method of integration, isn't it? So once again, if we say that, let's say the block has undergone a certain displacement x, it has reached somewhere here at a position x. At this position, the spring force acting will be kx and the external force is F, and if we assume that the block undergoes a very small displacement dx at this point in time, the small work done dw by the force F will be F dot dx, F dot dx. Understand that both the force, external force F, and the displacement dx are in the same direction. So the angle between them will be 0 degrees, and this can simply be written as F dx then. because cos 0 is 1. And now all we need to do is substitute the value of f, ma plus kx dx. This is our small work done dw. And how do we find out the total work for a displacement d? Just all we need to do is integrate this expression. dw, integral of that will be nothing but integral of ma plus kx into dx, and the limits of integration of x will be from 0 to d, right? The block has been moved by a distance d. And now we just need to solve this expression. So this will be, we can open up the bracket to get ma dx, integral of that from 0 to d, plus integral of kx dx from 0 to d. Integrating both, integral of ma being a constant will stay as it is, and the integral of dx will be simply x from 0 to d, plus integral of x dx will be x squared by 2. So k into x squared by 2, 0 to d. Putting the limits now, we can get the final answer. So this will be ma into d minus 0, which will be d, plus k by 2 into d squared minus 0 squared, which will be d squared. So this becomes the total work done here, right? So this is how we can work with the spring force to find out the work done by the spring or by other forces also. Let's discuss one more aspect now. Work is dependent on the frame of reference from which we study it, from which we try to find it out. Work is frame dependent. Let us see how. There is this block of a certain mass, and there is a force F acting on this block towards right, due to which the block undergoes a displacement S towards right. Okay. Now this displacement S is as observed by an observer who's standing on the roadside, who's standing still with respect to the ground and observing this motion of the block happening towards right, right? Can we say according to this observer, we can call him observer 1. The work done by the force F as seen by observer 1 will be the force acting on the block times the displacement of the block times the cos of the angle between the two, force and displacement, which is 0 degrees. So it is simply F into S, right? Instead of this observer, now we have another observer who's standing on this block and observing the things happening. This is observer 2. According to observer 2, how do you think the motion of the block will be? Do you understand now? Since the observer himself is a part of the block, he is standing on the block, as seen by him, the block does not undergo any displacement, right? From the frame of the observer 2, there is no displacement that the block undergoes, and hence the work done by the observer 2 will be force into the displacement, which is now 0. That becomes 0, right? So the work done will be 0, and that happens because S, the displacement of the block as seen by observer 2, is 0. So understand that force though does not depend upon the frame, the displacement part, the displacement of any system, it's dependent on frame, and hence the work done which depends upon that displacement is also frame dependent.